Let's say you build a machine learning system to navigate a highly specific library. To train it, you map the exact dimensions of the space, the precise placement of every book, right down to the floating dust motes. When the model runs its first few simulations, it absorbs all those parameters flawlessly. It avoids every chair leg and calculates the optimal paths. A data scientist looks at that 100% accuracy score and sees a victory. But we don't build these models to live in a controlled simulation. We build them to operate in the real world. So we take our perfect system and we place it in the room right next door. Instantly, it crashes into a table. It spins in circles, scanning for a missing bookshelf. The system is unusable because its navigation rules were hard-coded to a specific coordinate map that no longer exists. Our model failed because of a trap called overfitting. It never actually learned the general rules of how to navigate a physical space. It simply memorized the specific room we built for it. To understand why this happens, we need to look at how a model categorizes information. At its core, a machine learning algorithm often works like a decision tree, splitting data by asking a series of yes or no questions. If we let a tree run without limits, it will chase that perfect training score by generating thousands of bizarre, hyper-specific parameters. It stops asking, is there a wall here, and starts asking, is there a 3-inch scuff mark on the floorboard at a 45-degree angle? We can see exactly what this does to our data. This is a scatter plot representing the information we feed an algorithm. The blue dots follow an upward trend. That's the true signal, the actual law of reality we want the machine to learn. But there's also random variation in the data, which is just noise. A successful algorithm draws a smooth, elegant curve straight through the center of the cluster. It ignores the outliers because it understands that the broader trend is what actually matters. But an overfitted model has too much capacity. Instead of capturing the trend, it contorts itself into a jagged, chaotic line to touch every single stray point on the board. It has gerrymandered its logic to achieve a flawless score on the data it already knows. In doing so, it has completely confused meaningless random noise with the actual rules of the system. We tend to think that adding more parameters makes a machine smarter, but the math shows us that unchecked complexity actually destroys a model's ability to comprehend the bigger picture. Because training scores can lie to us, data scientists have to enforce a reality check before a model is ever deployed. They do this by physically cutting their dataset in half. They take the bulk of the data and use it to train the algorithm. The rest is locked away in a vault. We call this the test set, and it acts as a simulation of the unpredictable future. The model is strictly forbidden from seeing it during training. When we finally introduce this hidden data, we can chart exactly when a system stops learning and starts memorizing. This graph measures our model's complexity on the bottom against its prediction error on the side. As we add more branches to our decision tree, its error rate on the training data drops, plummeting towards 0. It is perfectly mapping out the past. But when we ask it to make predictions on the hidden test set, the results diverge. The error drops initially, but as the model becomes overly complex, the error on the new data suddenly spikes violently upward. This shaded zone is the generalization gap. It tracks a system that has perfectly indexed the past while failing to account for any data it hasn't seen before. Closing that gap requires an engineering fix. We have to intentionally restrict the model, penalizing its complexity so it is forced to focus entirely on the macro trends. One common method is pruning. We go into that tangled, overgrown decision tree and snip away the excessive lower branches. We reduce its capacity so it can only form the most essential, robust rules. Engineers also use techniques like cross-validation, where they repeatedly slice the data into different combinations. This forces the model to constantly prove itself against dozens of mini futures during the training process. When you run these diagnostics, you realize that in machine learning, a suspiciously perfect training score is never a victory. It is a glaring warning sign. Success in machine learning depends entirely on generalization, the ability to accurately navigate an environment the model has never encountered before. But that raises a new problem. If we aggressively prune our tree and strip away its complexity, what happens if the model becomes so simple it can't recognize the shape of the room at all?